In the last part, we talked about finding volumes by slicing with some general cross-section shapes, semicircles, squares, triangles. Now we're going to consider cases where we're going to restrict ourselves to this particular case where we have discs or generally these washers, donut shapes. And the idea is that we're going to be rotating a region in the plane about an axis to create some sort of cone-like circular shape in some. And so the primary idea is to think that if we have a strip represented by this silver pen here, and I rotate it around an axis, say, rotate it around my thumb, then that traces out a circle. Now note here that the pen is perpendicular, is orthogonal to the axis created by my thumb here. So when we slice by discs and washers, we want our representative strip to be perpendicular to the axis of rotation. And the primary principle here for computing these areas that we're going to be thinking about areas of circles, okay, pi r squared. So now let's go ahead and consider a few examples here. So we have a region in the plane here, which I'll shade in magenta, bounded by the parabola y equals x squared, bounded by the vertical line x equals 1, and the x-axis y equals 0. And take note here that I'm going to rotate this region around the x-axis. So what that means is I'm going to take this magenta shape here and rotate it around this axis here. So I'm going to draw an arrow to represent that. So we have our region sketched here. And just for illustrative examples, I'll go ahead and kind of draw a sketch of what the solid should look like. So here's our parabola, sort of, our vertical line x equals 1. And we're going to rotate this around the x-axis. So we get like this sort of conical shape here, this bell-shaped thing here, if you know about brass instruments. Almost looks like the bell of a trumpet or trombone. And we want to figure out how to find the area of one of these little cross sections here, which I'll shade in this light blue. And then we'll try to figure out how to find the volume of such an object. Well, the cross sections here are circles. Okay, just go back again to the illustration with my silver pen here. The cross sections trace out circles. We need to find the radius of such a circle, and then we can find the area of such a circle. So let's go ahead and draw a representative strip here. So let's take this strip here. And this strip has some length, which will in turn represent the radius of our disk. And so we ask ourselves, how do we find the radius of our disk? Well, we go back to our area between curves principle, top minus bottom. So at any x here, our radius here, but actually in first, let's go ahead and write down what the volume formula. That's going to be our general volume formula is going to be pi times the integral over an interval a to b, and then it'll be the radius squared dx. This is for when we have disks where we have no empty portion on the inside. So now how do we find this radius? Well, this curve here is y equals x squared. And we have y equals 0 here, the x-axis. And the radius here is x squared. So at any x, I can figure out what the corresponding radius of a disk is. And now it's straightforward to figure out how to find the volume. So to find the volume here, go ahead and keep that there. To find the volume, pi times an integral of the radius squared. But where are we integrating over? Well, we're going from x equals 0, that's this intersection point here, to x equals 1, which is the vertical line here in our boundary. We're integrating from 0 to 1. And it's straightforward. Power to a power makes this a superpower, so we multiply the exponents 4. And as usual, we do the power rule. Add 1 to our exponent. So pi times x to the 5th over 5, evaluated between 1 and 0. And for the sake of completeness, we'll go ahead and write down get here, 5th over 5 minus 0 to the 5th over 5. Well, 1 to the 5th is just 1, so we just have pi over 5. So a very simple example of how to find this volume using uh, slices via disks. Okay, here we're still using our same principle of integrating our area function. Now we're using a special area function here just for circles. Let's move on to our next one here. Now let's consider this region here. It's bounded by the parabola in purple there. Okay, the line y equals 4, that's the top line in black there. X equals 0, the x-axis, the y-axis. Okay, so let's put that in there. So x equals 0 is this line here, the x-axis, the y-axis, excuse me. And x equals 2 is this golden line. We're going to rotate it around the y-axis. Let's go ahead and draw that in. Y-axis is again the line x equals 0. So what is the region that we're worried about here? Well, we're going to follow the boundary here. So the parabola, y equals 4, x equals 0, x equals. So we are talking about magenta region here. Now, in part 3, we're going to learn how to find volumes using the method of shells, which would probably be a natural approach for this one. But to illustrate the point here for disks, let's go ahead and see how we would slice this. I want to use disks, okay, so let's remember. We want a strip perpendicular to the axis. A strip perpendicular axis of rotation. So in this case, our little representative strip here, because we're going around the y-axis, can be oriented this way. But that means I'm going to be integrating in y, so I need functions of y, and so I need to express the parabola in terms of a function of y. So y equals x squared. That means we're going to take square roots here, and we get x equals the square root of y. And we're only going to consider the plus branch of the square root because that forms the boundary, the right boundary of the curve, which is all that we were worried about. Okay. And now we have our radius here. Instead, here we're going to think right minus left instead of top minus bottom because we're integrating in y. So the radius here, for y. And now what's our integral going to look like? Well, remember that this strip moves up and down. So the lowest x value, excuse me, the lowest y value here is at y equals 0. The largest is at the top here, y equals 4. So the volume is pretty simple. Pi times the radius squared. So we're going to go integrate from 0 to 4. The radius here is square root y. Square that. Well, the square root of y squared is just y. This integral is just nice. Square root of y squared is y dy. So we'll get pi times y squared over 2 as our antiderivative. Evaluate that between 4 and 0. Okay, let's write down what we will plug in. 4 squared over 2 minus 0 squared over 2. Well, 4 squared is 16 over 2. That's 8. 8 pi is our desired volume. A very nice example here. Again, remember here that we're rotating around the y-axis. We want to use disks. We want to make sure that our strips, our slices, are perpendicular to the axis of rotation. Moving along here very nicely. Now let's consider this one here. We're going to rotate the region bounded by the two parabolas, y equals x squared, which is in this bluish purple color here. X equals y squared, which is in orange. And we're going to rotate this around the x-axis. Let's go ahead and draw that in. We're going to rotate around the x-axis, and it's going to be this region here between the two parabolas. Okay, again, I want to use disks. So I want to make sure I'm slicing perpendicular to the axis here. Okay, we can also phrase this in the future using shells, where we'll slice parallel to the axis of rotation. The method that you choose will, as you'll hear me say, out of convenience. Well, once again, we need to express everything in terms of a function of a single variable and the same variable. And the natural choice here is to make this as a function of x since we are slicing with vertical slices here. So this strip moves left to right. And so we're going to take this second parabola here, x equals y squared, and solve for y. Get y equals the square root of x. And we're only going to consider the plus branch here because the minus branch, the bottom branch, doesn't contribute to this area. Okay, now we're going to go ahead and figure out what our radius function would be. So our radius function here is just going to be the distance between the two curves. And again, we think area between top minus bottom. So the radius function here will be the top curve, which is the parabola here as we see in the picture. That's going to be square root x, minus the bottom parabola, which is x squared. Now, the next question that we have to ask ourselves is, well, where are the intersection points? You can definitely see that it's at 0 here, and we might be able to guess that's 1, but let's double check. Okay, so for the intersection points, let's do this in a different color. For the intersection points, we need to set the two curves equal to each other. Okay, now that we have two things set equal to a certain variable, we have y equals x squared and x equals y squared, we can substitute. Or we'll just look at this. We have square root x equals x squared, square both sides, x equals x to the fourth, and subtract. And I can factor out a common x there. So I have x times x cubed minus 1, 0. Certainly x equals 0 is an intersection point. Now we got to contend with x cubed equals x cubed minus 1 equals 0, which we could factor using this difference of cubes formula, or because this is just something, a single thing in x equals a number, have x cubed equals 1. When we take cube roots, get x equals 1. So right there, we get our two intersection points, and now we are ready to set up our integral. For our volume here, pi times the integral from now 0 to 1 of our radius function squared, square root x minus x squared dx. And now we'll have to multiply out and be very careful using our favorite pattern, the perfect square binomial. So the first thing squared, that's just x, minus 2 times the first times the second, so 2 x squared square root x. We'll tidy that up in a bit. And then plus the last thing squared, plus x to the fourth dx. Now let's tidy up that middle term here, keeping in mind here that square root of x, remember, is x to the 1/2. And when I multiply with exponents, I'm going to add the powers. So x squared times square root of x, that's x squared times x to the 1/2. So what do we get there? Well, 2, write that as 4 over 2. Let's write that here on the side. X squared times square root x. We have x to the 4 over 2 times x to the 1/2. And 4 plus 1 is half plus x to the fourth dx. And once again, we use our power rule. Most basic integration formula that we have, the power rule. Everything works out nicely here. X squared over 2. And then minus, let's be a little careful here. Let's go ahead and spell this out. 2 times x to the 7 over 2. We add 1 to the exponent. Divide by 7 over 2. And then plus x to the 5th over 5. Evaluate this between 1 and 0. And you should be able to see here that when you evaluate this at 0, you get 0. Just lucky for the function that we have. Let's go ahead and clean up this middle one here. And remember that we're just going to be plugging in 1 and plugging in 0 and subtracting. But because evaluating this at 0 gives us 0, okay, I'll just go ahead and write down what we get for evaluating at 1. So we'll have pi times 1/2 minus, well, 2 times 1 over 7 over 2. Okay, the way we divide fractions, keep, change, flip. So we'll keep the 2, change divide to multiply, and then instead of dividing by 7 over 2, we'll multiply by 2 over 7. Like 7 over 2. there. Then that's a 1. Okay. X, 1 to the 7 over 2 is just 1. Then plus 1/5. And then again, subtracting away the evaluation at 0, we just get 0. So let's tidy this up. We have 1/2 minus 4 over 7 plus a fifth. Okay, you are free to use your favorite calculator of choice here when preparing here. So when we go ahead and type all this in to our favorite device, we'll get one nice little fraction. That inside part is just 9 over 70. So we just get 9 pi over 70 as our volume. So straightforward. The only hard part here was, of course, okay, dealing with that middle term there, that x squared square root x. So if we remember our basic patterns, we can go ahead and tackle anything. All right, let's go ahead and move on to the next one. Okay, once again, another simple thing here. Find the volume of the solid obtained by rotating this region. So y squared equals x, again, another parabola. The line x equals 2y, and we're going around the y-axis. Okay, so let's go ahead and highlight that here. Around the y-axis, we're going around this way, and our solid region here, let's go ahead and color that in our favorite magenta. Now, since I'm rotating around the y-axis, and this whole set is on disks, once again, we're going to slice perpendicular to the axis of rotation, meaning our slices will look like this. This is our strip. And if you'd like, think about what the solid will look like. Okay. Rotate this around here. So around the top, it's going to look something like this. Okay. Here's like a little representative little washer there. It's called a washer because you have the empty part in the middle there. Let's go ahead and draw a side view cross section. Yes. So there's our circle, a little circle here. We're only worried about this part here in pink. Okay, where the outside radius here. Okay, outside radius from the center to the outer edge there. Okay, that's the furthest away. In this case, that's the line. That's the purple. Okay, and then the inside radius, smaller one, is the orange parabola. Okay, so we have two curves here, x equals y squared. Go ahead and color them in. X equals y squared. And we also have x equals 2y. Well, which curve is the outside curve? Well, that's the one that's furthest away. Think about area between curves once again. Here, since we're slicing and integrating in y, we want to think right minus left. So the curve on the right is the outside one. Let's think about it. The curve on the right is the outside one, 2y. The curve on the left is the inside one, y squared. So how do we find the area, the solid area for this washer, this donut shape? Well, the area here, let's do magenta, going to be pi times outside radius squared. That's the entire circle. And then we want to take away the inside circle. So write as little r squared. Well, in this case, okay, well, we can factor a pi out. So outside squared, the biggest one. Here it's the right squared. So 2y squared minus inside squared. Y squared squared. And we can go ahead and tidy this up. 2y squared, that's 4y squared, minus 1 to the fourth. That's our area function for one cross section. And all I need to do is figure out the intersection points and integrate. Well, let's go ahead and find the intersection points here. Okay, let's set these two equal to each other. We have y squared equals x, 2y equals x, so we can go ahead and write following y squared 2y. And let's go ahead and subtract and move stuff over. Y squared minus 2y equals 0. Once the intersection, right? factor y times y minus 2 equals 0. So y is equal to 0. We get y minus 2 equals 0 by our zero product property that we've been using. And that means y is equal to 2. So we're integrating from 0 to 2. So how do we set up our volume? Well, in the same way that we always did, we take our cross-sectional slice, we figure out that area, and we integrate that area function. Here, it's a difference here because we're taking away a centerpiece that has a hole. The volume will be pi times the integral from 0 to 2 of our area function here, which we already did all the squaring and everything here. 4y squared minus y to the 4th dy. And it's just more power rule stuff, right? Well, pi times an antiderivative of 4y squared, we add 1. 4y cubed over 3, divide by the new power. Same thing here, add 1 to the power, divide by the new power, y to the 5th over 5. I'm going to evaluate this between 2 and 0. Once again, when we evaluate this as 0, we get a nice number, 0. So we'll just go ahead and evaluate at the top there. 4 times 2 cubed over 3 minus 2 to the 5th over 5. Well, let's see what we get here. Well, 2 cubed is 8. 8 times 4 is 32. And 2 to the 5th, well, that's 8 times 4, 32. Have this number here. Okay, we'll get a number that's something over 15 here. Okay, we can go ahead and compute that easily. And just using our tools here, 32 over 3 minus 32 over 5 comes out to be 64 over 15, so our volume is 64 pi over 15. Okay, so this one had a small change here, because now the region that we form by rotating this thing has a hole in the middle of this empty space here. We're only concerned about this magenta region here. Okay, so we got to think outside squared. Let's go ahead and make that here. Outside squared minus inside squared is the idea here. Okay, and it follows from top minus bottom, from right minus left. Okay, if we were rotating the same region around the x-axis, okay, we'll still have a hole there, as you'll see in the picture. Okay, we still have this hole here. Okay, but the idea remains the same. Outside squared minus inside squared. Top minus bottom. Big minus small. Okay, we're making very good progress here. Take a look at this one here. Solid formed by rotating the region bounded by y equals e to the x, y equals 0, x equals 0, and x equals 1 about the x-axis. So we're going around the x-axis here. Call that in. So y equals e to the x, our favorite exponential function. Y equals 0, that's the x-axis. X equals 0, that's the y-axis. X equals 1, that's that golden line. So our region that we're worried about is here. And let's draw in a little representative strip here. Again, going around the x-axis, we want this strip to be perpendicular to the axis of rotation. Draw that here. Okay, and now we think about what our radius is going to be. Well, the radius will be this distance here, top minus bottom. Draw that in, radius. Top, e to the x, minus the bottom, 0. Okay, that's just e to the x. All right, and where are we integrating over? Well, it kind of is suggested here from x equals 0 to x equals 1. And you can also see that as well, right? By just looking at the picture. But when you draw the picture out, okay, you have to do this with a picture. You can't just go off of verbal description. You'll see that we will be integrating from 0 to 1. And so how do we handle this? Well, let's go ahead and write out the integral for the volume. Pi times the integral from 0 to 1 of our radius squared. All right, once again, power to a power makes it a superpower. So in the inside, we just have e to the 2x. Now, a question comes, how do we evaluate this? Well, this will be a good time to review our basic U substitution here. There's a way you can kind of do this without the substitution, but this is bookkeeping that goes on in your head when you do it without the substitution. So We know how to integrate e to the x alone, but what about e to the kx? Okay, here k is 2. Well, let's go ahead and do a u substitution here. We're going to change variables. We'll let u equal 2x. And so when I will find a differential, we take derivatives on both sides. Du is equal to 2dx. My integrand doesn't have a 2dx, it just has a lone dx. We'll just go ahead and solve for dx here. So I divide both sides of that previous line by 2, get 1/2 du equals dx. All right, so that's fine. But remember, when we do u substitution, like I said in that video, okay, when we do u substitution, we are changing units. We are changing variables. So these limits of integration are no longer valid. We have to change them. So when x is equal to 0, we need to find the corresponding u just by plugging in. 2 times 0 is 0. And when x is equal to 1, u is equal to 2 times 1, which is 2. So our new integral here of pi times the integral now, instead of 0 to 1, it's 0 to 2. We're changing units here, changing scale. E to the 2x, that's e to the u. Then I have 1/2 du for dx. So 1/2 du. And now I know how to integrate e to the x. It's just itself. So go back here. Pi times 1/2 e to the u. Evaluated between 0. Now be careful here, because evaluating this at 0 doesn't give us 0. What it does give us is something nice. Pi times 1/2 e squared minus 1/2 e to the 0. E to the 0 is 1. So when I clean all this up, I just get pi times 1/2 e squared minus 1/2. And that's our volume. That's our volume right there. Pretty nice, right? Okay. We're almost done with this set. We got a few more. Okay, this one just shows you how you can use that technique of integration, change of variables, use substitution, to simplify the integral. Now, try to see if you can figure out a pattern for when you compose a linear function inside a bigger function and see what the use substitution pattern is. Okay, that'll be a good exercise if you haven't done that already. So now this one may look a little daunting, but it will come out nicely in the end, although we won't get a nice exact number in the end, but it's still something that we can use. We want to find the volume of the solid here, bounded by y equals secant x in purple, y equals 1 in orange, x equals -1, and x equals +1 about the x-axis. So the region that we're worried about here, and I'm rotating this, again, around the x-axis. Okay, so let's draw in our little slice. You can kind of get an idea for what this thing would look like. Okay, now we need to think about, again, what is our radius function? We think top minus bottom. So our radius function here will be composed of two parts. We have the part on the outside, okay, which is going to be the secant. So let's look at the area function here. Top squared, so secant squared, minus the bottom squared, 1 squared. Okay, well, 1 squared is just 1, right? Now, some of you may be tempted to rewrite this in a certain way because you might remember the trig identity. Secant squared minus 1 is tangent squared. I'm going to tell you to leave it like this. For the moment, we won't know how to integrate tangent squared. Okay, we're going to need some extra techniques for that, but this keeps it in terms of things that we know, in terms of functions whose antiderivatives we know. Okay, well, let's go ahead and look at our region of integration again. We got to find the intersection points. That's kind of given to us in the picture. And most of the time, whenever you're given like a lot of vertical or horizontal lines, those tell you your region of integration. Okay, so our volume here, well, I should say here our area function is pi times this, pi times that. So the volume here is going to be the integral pi, okay, times, so that's integral from -1 to 1 of your radius function, secant squared x minus 1 dx. Okay, well, we need to remember, okay, that the derivative of tangent is indeed secant squared. So that tells us that the integral of secant squared is tangent. Remember that derivatives and integrals, okay, from FTC, we'll go back and watch that if you haven't already, that derivatives and integrals undo each other in a sense. So we'll just have the following: pi times tangent of x minus x, between 1 and -1. Now, you might be asking yourself, but I don't know what the tangent of 1 is. That's okay, you can just leave it as tangent of 1, same with tangent of -1. Something nice will pop out of here too. We'll have pi times, well, tangent of 1, which is a number, minus 1, and then minus tangent of -1 minus a -1. Okay, let's go ahead and tidy this. Pi times, well, let's see. I'll have tangent 1 minus tangent of -1 just by shuffling some terms around. Then I have minus -1, which is a plus 1. Okay, but then I have another minus out there, so that's a -1. -1 minus 1 is -2. Now, there is a way that we can simplify those first two tangents together, okay? But this is an acceptable answer. But if you remember a basic thing from trig, and that's okay if you don't at the moment, okay? Tangent is an odd function, which means tangent of minus x is the same as tangent x minus tangent x. So I can use that here to write tangent of -1 as negative tangent 1. That helps me because the minus on the outside there gets absorbed into a plus. And now I can collect like terms here. 2 tangent 1 minus 2. That's our volume. But like I said, this one here as well, this one is okay to leave it. So a little unorthodox. Still something that we can handle. All right. Now, let's move on to these last ones here, okay? This one asks us to set up, not evaluate the integral for the volume. And it's a good thing to understand how to set up these integrals, but maybe for the moment you don't know the technique. This is again where we choose things out of convenience. Okay, we'll soon learn that for this one, shells is the way to go, but of course we won't have the techniques to handle that one yet. But let's think about it here. Okay, we're going to bound it by y equals log x, that's purple, x equals 1, that's the black line, y equals 1. Okay, so we are concerned about, let's see, let's take a look here. Log x, x equals 1, y equals 1. So it looks like we have this thing here, this region here. And at the moment, it doesn't really look like it makes sense to us, right? The region bounded by the curves y equals log x equals 1, and y equals 1. Ah, this is where we got to be careful and read the questions. So let me go ahead and outline the curve entirely in, say, red. Okay, so y equals log x equals 1, and y equals 1. So that red outline forms our curve. It forms our solid body. We're going to rotate this around the x-axis, okay? And let's draw in our little representative strip. And so now we follow the mantra, top minus bottom, outside minus inside, okay? Outside squared minus inside squared, big minus small, okay? Well, top curve is 1, the bottom curve is log x. So we'll set up our area function. That will be pi times top thing squared, 1 squared, minus bottom thing squared, log x squared. Okay? Well, now we just write down the integral for the volume. It'll be pi times the integral from, well, From where to where? I know it's from going to start at x equals 1, but where do these two cross? So I need to figure out where log of x, natural log of x, is equal to 1. And we remember that log and e are inverse functions. And we'll see that x equals e. Integrating from 1 to e, that magic number e, okay? 1 minus log of x squared dx. Now, for the moment, we don't know how to handle this integral, especially in particular the integral of log x squared. We'll need a technique called integration by parts, which we will soon learn. Okay, but once we have that, this integral is doable. That's how we handle this one. Just a setup. Once you set it up and you know how to do the integrals, everything follows. Let's do this last one here. Now we got something a little funkier. Let's go ahead and trace out like we did before. Cosine of x forms a boundary. Y equals 0 forms a boundary. X equals 0 forms a boundary. And x equals pi over 2 forms a boundary. So it's this body here. And we're going around the line y equals minus 1. Okay. So now we're not going around a particular one of the axes, but we are going around a different horizontal line. So this one's going to take a bit for us to think about. Okay, again, we want to think about outside squared minus inside squared. So let's go ahead and draw in the strip here. And I'm going to try my best to draw in like a representative cross section. Okay, well, I want to figure out the distance from the axis of rotation, the top, and the axis of rotation to the bottom. Well, let's think about where the strip is. The top of that strip hits the top boundary curve, which is cosine of x. And the bottom is the line y equals -1, which is fixed. So to find our distance, it's again top minus bottom. Cosine of x minus a -1. Careful, because that minus is built in there. Okay, so that's just cosine of x plus 1. Okay, very nice. Now, does that make sense? Let's ask ourselves this. If I start here at x equals 0, what's my radius? And does it make sense? Well, cosine of 0 is 1. 1 plus 1 is 2. And this point is, of course, 2 units away from x equals -1. Y equals -1. You have 1 there. And then you have the extra 1 there. 1 plus 1 is 2. But note again that this black strip varies. Okay, the black strip will vary. It'll go from left to right, so that height changes. So what's our area function here? Let's write that down. Pi times the outside squared, cosine of x plus 1, minus the inside squared. Okay, well, the inside distance, 0 minus -1, that's just 1. So for the moment, let's go ahead and write out our area function like this, cosine of x plus 1 squared minus 1. Okay, and what's our volume? Well, we're integrating this area function. Now it's from 0 to pi over 2. Again, whenever you have like these horizontal or vertical lines as boundary curves, that tells you kind of where you're integrating over. Okay. Now we'll have cosine of x plus 1 squared minus 1 x. Now, for the moment, we don't quite know how to handle integrating. Well, when we expand this out, we'll get cosine squared, and we don't quite have the tools to integrate that just yet. Okay, we'll need to call some trig formulas here, some trig identities, especially the double and half angle formula. Okay, but for the moment, this is the volume that we need. This is the integral that we compute to find the volume. So the primary thing here is to keep thinking about your pictures, right? Draw them if you don't have them. Sketch out one of your cross sections, your pieces, and then just follow the principle. Area of a circle here, just think in general. Outside squared minus inside squared, and that comes from top minus bottom. So I hope you enjoyed this one. And in part 3, we'll now talk about the other way that we compute volumes which is when we use shells. See you in the next one.